In this video, we're going to work through an example problem that uses the van der Waals equation of state. So for the example, we say in an industrial process, nitrogen gas is heated to 500 Kelvin at a constant volume of 1.000 cubic meters. The mass of the gas is 92.4 kilograms. It asks us to use the van der Waals equation to determine the approximate pressure of the gas at its working temperature, and gives us the van der Waals constants. Okay, so to begin with, we should write down the van der Waals equation. So this is pressure is equal to nRT over volume. That's the same as the ideal gas law. And we're subtracting from the volume a fraction of the number of molecules according to the amount of space that they take up. So that's volume minus the constant B times the moles of gas. We also subtract from that a factor that accounts for the attractive forces between the gas molecules, which is the constant A multiplied by the molar density squared. Now, writing down the values that were given by the question, we're given a value for temperature at 500 Kelvin, and we're given the volume at 1.000 meters cubed. We're not given the amount of gas, but we are given its mass at 92.4 kilograms or 92,400 grams. Now we just need to multiply that by its molar mass to find the number of moles. Remembering that it's nitrogen gas, not just nitrogen atoms, so its molar mass is for N2, 28.014 grams, which gives us 3,298.4 moles of N2. So we say the pressure is equal to 3,298.4 moles. And we make sure that we're using the right value for the gas constant. In this case, it gives us the volume in cubic meters, but let's convert that into liters just for fun so we get an answer in atmospheres. So that our value that we're going to use is 0.08206 liter atmospheres per mole Kelvin. And we're at 500 Kelvin divided by, this is now 1,000 liters. And we subtract out 3,298.4 mole times that constant B, which is 0.0387 liters per mole. And it's important here not to forget the second term, so here we have 1.352 liters squared atmospheres per mole squared multiplied by the moles, which again 3,298.4 moles per 1,000 liters. Here we see the advantage of converting into liters and atmospheres, since the constant in this case was given to us in liters and atmospheres. Okay, we'll take that and square it. Okay, and giving ourselves a little bit of extra room, we can now write down the solutions to the two terms. So for the first term I have 155.136 atmospheres minus 14.71 atmospheres for the second term, which gives me a grand total of 140.4 atmospheres, which is the same as 1.423 times 10 to the 7 pascals. So pretty high pressure process. And as usual, we'll throw a box around that to show that it's our final answer. So nothing tricky about this question, just a fairly straightforward van der Waals type question. Seeing how we're going to apply the two constants and making sure that all of our units correspond to one another.